vertical, horizontal asymptote, and then domain of rational function. So today, whether we like it or yes, we are going to be looking at limit. Sorry about that. I have sore throat, so my voice is a little bit, it sounds like I'm speaking through my nose. Forgive me for that. All right, so today, like I mentioned, we're looking at limits, but before we do that, let's try and see if we can understand it without the mathematics aspect like we've been doing so far. So when we talk about limits, we are looking at behavior. All right, so the word here is behavior. Limit means we are looking at behavior of a function, since functions are what we are using in studying calculus. We're looking at the behavior of a function as the variable in it approaches a certain number. Now, there are two limits that we are going to take under consideration. Whether first is whether the variable in it, which is x, is approaching a, and then the other is when the variable x is approaching plus or minus infinity. So when x is approaching a, we say that we're looking at the behavior of the function as x is approaching a point. And then when we're looking at limits as x is approaching infinity, then we say that we're looking at the asymptotic behavior. All right, so asymptotic means that we're looking at extreme ends, which is plus or minus infinity. But when we are looking at limits at a point, then it means that the variable in our function, which is f of x, the variable in the function, which is x, is approaching a number a. So basically, how we understand limits when x is approaching a number a is, let's go back to our number line. All right, so we have a here. There are two ways that the variable x can approach a. The variable x can approach a from the negative infinity direction, and then we can also approach a from the positive infinity direction. This is what we mean. We're looking at the behavior of the function f of x as x is approaching a number. The number a here could be any number at all. And so since the number, we can approach the number from both directions, whether from the negative infinity direction or from the positive infinity direction, it means that we're going to look at the number that the f of x will be approaching. That will represent the limit of the function. An example is, consider somebody seated in front of you. Okay, consider somebody seated in front of you. If you move your hand from the right-hand side closer and closer to the person's face, what will be the behavior of your hand? The behavior is that you are definitely going to stop because of human rights violation. Please, can you mute your mics? I get echo. So the behavior is that as you move your hand from the right-hand side closer to the person's face, you are going to stop. The same way you can move your hand from the left-hand side towards the person's face. So if you are studying the behavior of the movement of your hand from both the right-hand side, so this is the person's face, we can move our hand towards the person's face from the right-hand side. We can also move our hand towards the person's face from the left-hand side. Limit means is the behavior of the movement of our hand from the left-hand side, the same way the behavior will be from the left-hand side. All right, so we are looking at what will happen as our hand gets closer and closer to the person's face from the left and then from the right. If from the left, the behavior is the same, all right, if from the left, the behavior is the same as the behavior from the right-hand side, then it means that whatever we are approaching is indeed the limit to our hand. The same way we study limits in mathematics. We are looking at the behavior of the function f of x as the independent variable x approaches a certain number. We are looking at two things here. One is when x is approaching a point, and then the other is when x is approaching plus or minus infinity. This part here, we'll look at it later on. But for the time being, we are looking at the limit at a point, meaning that that x, which we have been having in our function so far, is approaching a certain number. The behavior might change. In some cases, the behavior might not change. In other cases too. Now, x can approach this number a in two directions because we are working in 2D, in two directions. From the positive direction, we can approach a. From the negative direction too, we can approach a. X can approach a. We want to look at how the function f of x will behave, meaning what will be the value of f of x as x approaches a from the left-hand side, as well as from the right-hand side. For the limit of f of x to exist, the behavior from the left must be the same as the behavior from the right. Meaning, as x is approaching a from the right-hand side, if the value of f of x is not the same as x approaching a from the left-hand side, then it means that the limit of f of x does not exist. For the limit to exist, the f of x, the value that the f of x is approaching in this direction must be the same as the value that f of x is approaching in the positive, from the positive direction. Let's take it to our figure here. For the face to be the limit, it means that the behavior we exhibit with our hands as we approach the person's face from this direction must be the same behavior from the left-hand side direction. If the behavior from this direction is not the same as the behavior from this direction, then indeed the face is not the limit. For the face to be the limit, the behavior in both directions must be the same. Otherwise, the limit does not exist. So given f of x, if I want to evaluate f of x, if I want to determine the limit of f of x, it is not the f of x moving, no. It is the variable within the f of x that is going to dictate what the f of x should be. All right, f of x on its own does not have any value. It gets a value when we say that let x be equal to 1. Then f of x will move to position f of 1. When x says today I am 2, then f of x will move to position f of 2. So f of x on its own cannot vary. It varies based on what the x is. And so if we're looking at the limit of the function, it means that we are looking at the value that f of x is approaching as the variable x is approaching a certain number. So for instance, given f of x as x is equal to x squared, if we want to evaluate the limit as x, which is the independent variable, approaches 2, 2 is over here, we can put 2 randomly on our number line. There are two directions in which x can approach 2. X can approach 2 in the positive direction. X can also approach 2 in the negative direction. The value that f of x approach or f of x becomes or get closer and closer to as x gets closer and closer to 2 from the positive direction and then from the negative direction. If the values that x is approaching is the same, then that value becomes the limit of the function. So from the positive direction, if we are moving towards this direction here, what are some of the values that we'll get to before we get to 2? There are several values here. The x is approaching 2. So we don't need to pick numbers that are far away from 2. No, we're looking at the behavior of the function f of x as x approaches positive 2. So we look for some of the values that are closer to 2 as I'm moving from the positive infinity direction. Some of the values are the 2.01. Another will be 2.001. Even way closer will be 2.0001. These are some of the numbers that are closer to 2. You could also pick 3, but 3 is far away from 2. We want to look at the behavior of the function in the vicinity of positive 2. So we look for vicinity of positive 2 from the positive infinity direction, and those some of the numbers are these. Then we also pick some of the numbers from the negative infinity direction. And some of the numbers from the negative infinity direction are maybe 1.9. We could also have 1.99. And then we could also have 1.999. These are some of the values that are closer to 2 from the negative infinity direction. You could also pick 1, or you could pick -1, but those numbers are far away from 2. We are looking at the behavior within the smallest neighborhood of 2. So we don't have to pick numbers that are far away from 2. All right, so we look at these values of x and see how the f of x will behave as we get closer to 2 from this direction, meaning we are going to find the value of f of x as x is 2.01. Find the value of f of x as x is equal to 2.001. Find the value of f of x as x is equal to 2.001. And see how the f of x will behave. Will it be approaching a certain number? We put that down. Then we come to the negative infinity direction. When x is equal to 1.9, what will be the value of f of x? When x is equal to 1.99, what will be the value of f of x? When x is equal to 1.999, what will be the value of f of x? If in this direction, f of x is approaching a specific number, and if that specific number is the same number that f of x is approaching in this direction, then that number becomes the limit of the function f of x as x approaches 2. Because what we have here is not x equal to 2. What we have here is as x get closer and closer to 2, what value does f of x also get closer and closer to? We don't want the exact. We don't want to get there exactly, but what will be the behavior as we're getting closer and closer to positive 2? All right, so let's put this in a table form. Let's do the left-hand side first, and then do the right side first, and then see the value of f of x. So see what value f of x will be approaching. So from the left, which is from the negative infinity direction, some of the values of x that we picked were 1.9. We also picked 1.99, and then we also picked 1.999. And then let's look at the behavior of f of x, where f of x, the function we picked was x squared. All right, let me see if I can get a calculator by so I don't. All right, so when x is equal to 1.9, when x is equal to 1.9, f of x is equal to 1.9 squared. So 1.9 squared, that would be 3.61. Then we go to the next number. When x is equal to 1.99, f of x will be equal to 1.99 squared. Okay, so 1.99 squared, that will give us 3.9601. Then when x is equal to 1.999, f of x will be equal to 1.999 all squared. So 1.999 all squared will give us 3.996001. So these are the value of f of x as x is approaching 2 from the negative infinity direction. So as x is approaching 2, we notice that f of x is approaching 4. All right, so as x is approaching 2, our f of x, which is the function we are using in this case here, which x squared, is approaching 4. Meaning, if we evaluate what f of x is from the positive infinity direction, some of the numbers that we picked for x from the positive infinity direction were 2.01, 2.001, and 2.0001. If f of x using these numbers is also approaching 4, then it means that the limit of f of x as x approaches 2 is 4. If the values are not the same, then 4 is not the limit of the function. In that case, the limit does not exist. For the limit to exist, the value from the left-hand side must be the same value from the right-hand side. All right, so we have 4 for the left-hand side. For the right-hand side, which is for the positive infinity direction, some of the values of x that we picked were 2.01. Then we also picked 2.001. And then we also picked 2.0001. Once again, we are going to evaluate what f of x is using these numbers. So here, x is also approaching 2 from the right-hand side. If the answers are the same, then 4 becomes the limit of the function. So when x is equal to 2.01, our f of x is 2.01 squared. So 2.01, that will be 4.0401. Then when x is equal to 2.001, our f of x is equal to 2.001 squared. So 2.001, that will be 4.004001. Then the last number where x is equal to 2.0001, our f of x is equal to 2.0001 all squared. So 2.0001 all squared, that will give us 4.00040001. All right, so let's see what this approach, as x is approaching 2 from the positive infinity direction, we also notice that f of x is approaching 4. So let's put the two tables together. As x is approaching 2 from the left-hand side, the value of f of x is approaching 4. And as x is approaching 2 from the right-hand side, f of x is also approaching 4. All right, so as x is approaching 2 from the right-hand side, f of x is also approaching 4. And as x is approaching 2 from the left-hand side, f of x is approaching 4. Right, so we notice that f of x, whether we are looking at x from the left or from the right, f of x approach the same number. Therefore, this implies that the limit as x approaches 2 of f of x, which is equal to x squared, is 4. And this is because the value of f of x from both sides, whether from negative infinity or from positive infinity direction, is the same value, which is equal to x. Let's look at another example. Maybe things will be clearer. Let's pick a different function. F of x is equal to...
Please, can you scroll up so we can write?
Oh, this was in the video I sent you.
Okay. Please, you can go ahead now.
Okay. So let's look at another example. F of x is equal to 1 over x. We want to evaluate the limit of this function as x approaches, say, 0. Let's pick a different number. It's always the case where x will approach 2. This means that we are going to look at the behavior of f of x as x approaches 0. We can approach 0 from 2 directions. So if I have the number line and I have 0 here, x can approach 0 from the positive infinity direction. X can also approach 0 from the negative infinity direction. Meaning we are going to evaluate what f of x is as x get closer and closer to 0, not x specifically being equal to 0, because the expression is when x is equal to 0. No, but as x approaches 0. All right, so we are going to pick some random numbers closer and closer in the neighborhood of 0 from the positive infinity direction. Then we're also going to pick some numbers in the neighborhood of 0 from the negative infinity direction. Evaluate what f of x will be. So what will f of x get closer and closer to as x get closer and closer to 0? So like I did earlier on, I have my positive infinity, I have my negative infinity in these directions. We can pick numbers that are closer to 0 from the negative infinity direction. Some of the numbers that we can pick are maybe negative 1 point. Oh, so I'm so far away. Negative 0.1. We can also pick negative 0.01. And then we can also pick negative 0.001. These are numbers that are closer to 0 from the negative infinity direction. Then we can also pick numbers from the positive infinity direction. Some of the numbers that are closer to 0 or in the neighborhood of 0 from the positive infinity direction, let's reverse the negation. So we can have 0.01, sorry, let me put 0.1. We can also pick 0.01, and then we can also pick 0.001. These are some of the numbers that are closer and closer to 0 from the positive infinity direction. Now that we have picked the random numbers, not necessarily random in that sequence, closer and closer to 0, we put these numbers into the function and then evaluate what f of x will approach. If the answers are the same from negative infinity and then from the positive infinity direction, then the numbers that we approach becomes the limit of the function. So from the left-hand side, some of the values that we picked for our x are the negative 0.1, negative 0.01, and then negative 0.001. Then from the right-hand side, well, let's do the left first. This is f of x is equal to 1 over x. So wherever we see x is where we are going to put the 0.1, negative 0.01, and then negative 0.001. So when x is equal to negative 0.1, our f of x is equal to 1 over negative 0.1. And that will give us, we are dividing by decimal, so that would be negative 10. Then when x is equal to negative 0.01, our f of x will be equal to 1 over negative 0.01, and that will be negative 100. When x is equal to negative 0.001, our f of x is equal to 1 over negative 0.001, and that will be negative 1,000. Looking at the way the numbers are flowing, if we had also picked that number 0.0001, then this would have been negative 1, like that. So as x is getting closer and closer, as x is getting closer and closer to 0, from the left-hand side, we notice that f of x is not approaching a specific number per se, but f of x is getting larger and larger. And it's getting larger and larger in the sense that the value is essentially negative. All right, but we look at larger and larger here. As the number is getting larger and larger, what number can we use to approximate it? Let's hold on for the time being. Let's also look at the values of x from the positive infinity direction and look at the behavior of the function. All right, so from the right-hand side, some of the values of x that we picked were 0.1, 0.01, 0.001. Let's add the last one, 0.0001. And then our f of x is 1 over x. So when x is equal to 0.1, our f of x is equal to 1 over 0.1. 1 over 0.1, that is equal to 10. Then when x is equal to 0.01, our f of x is equal to 1 over 0.01, and that will be 100. When x is equal to 0.001, our f of x will be equal to 1 over 0.001, and that will be 1,000. And then the last, when x is equal to 0.0001, our f of x is equal to 1 over 0.0001, and that will be 10,000. So from the right-hand side too, as x is approaching 0, our f of x is also approaching a very large number. F of x is getting larger, all right? But it's getting larger in the sense that the numbers here are positively large. If we compare the two, as x is approaching 0 from the left-hand side, f of x is approaching or is getting larger and larger in such a way that it is without bounds, right? The number as x is getting closer and closer to 0, f of x is without bounds. It's getting bigger and bigger, but it's bigger and bigger negative. As x is approaching 0 from the right-hand side, f of x is also growing larger and larger without bounds, but positively larger and larger without bounds. So from the left, as x is approaching 0 from the left-hand side, we notice that our f of x, which is equal to 1 over x, is growing larger and larger, but without bounds, all right? And a number which is larger and larger without bounds is said to be undefined. So it is getting closer and closer to negative infinity. Same way as x is getting bigger, as x is getting closer and closer to 0 from the positive infinity direction, f of x is also getting larger and larger, but without bounds. And it is positively without bounds. They are positive numbers. Now, for the limit of the function to be defined, it means that the value that f of x will approach from the left must be the same value that f of x will approach from the right. From the left, f of x approaches negative infinity. From the right, f of x approaches positive infinity. But we know that negative infinity is not the same as positive infinity. And so since the two sides are not the same, it means that the limit as x approaches 0 of
Does
f
not.
of x, which is equal to 1 over x, does not
Okay.
exist. All right, if the two values, assuming we got from the earlier example, we had 4 here, and then we had 4 there. The values all approaches 4. Therefore, the limit will be 4. But in this case, one of them is approaching negative infinity. The other is approaching positive infinity. So we notice that from the left, the function is behaving a different way as compared to from the right. Therefore, there is no consistency. And so the limit of the function does not exist because the behavior from the left is not the same as the behavior from the right, because the value from the left is not the same as the value from the right. Right, so from the earlier, we saw that the limit of f of x, which was equal to x squared, as x approaches 2 from the left and from the right, was equal to 4. And then from the second example, the limit of f of x, which is equal to 1 over s, as x approaches 0. From the left, we had minus infinity. However, from the right, we have positive infinity. Both answers are not the same. Therefore, this limit here does not exist. This here does exist, and the answer is equal to 4. However, if we put this long, tedious work aside, we realize that there is actually a simple shortcut. And that's simple, not necessarily a simple shortcut. Something so unique about the limit is that all we are doing so far is substitution. All right. If instead of going through all this long approach, because x is approaching a certain number, all we could also do is that you notice that from the first, where f of x is equal to x squared, as x approaches 2, you notice that if I do direct substitution, if I find f of 2, the answer will be 2 raised to the power 2, which is equal to 4, which is the same value as the limit. From the second example as well, we have f of x to be equal to 1 over x. As x approaches 0, the limit does not exist because the answer we got from the left was minus infinity, from the right was positive infinity. So the limit does not exist. However, if we find the value of f of x at exactly x equal to 0, then we are going to have 1 over 0, and 1 over 0 is undefined, meaning the limit is undefined. Therefore, the limit does not exist. All right, so we can, or we are allowed to do direct substitution. If you do direct substitution and the answer is the same as going through the long approach, then you are better off using the direct substitution. Meaning, yeah, we can bypass the long approach and then just evaluate the function f of x at the value that x is approaching. And if the answer is 4, then that represents the limit. If the answer is undefined, then it means that the limit of the function does not exist. So given I want to find the limit, yes, of f. Okay, let me finish with this one. Please jot down your question. As x approaches 3, we could do the long approach, draw our number line. I have 3 here. Pick numbers that are closer to 3 in this direction. Pick numbers that are closer to 3 in this direction. Put these numbers into the function. put these numbers into the function, and then look at the value that the function is approaching. That becomes the limit. We could also do direct substitution and find the functional value of f of x at x equal to 3. So we could have f of 3, which is equal to 3 raised to the power 3, and that is equal to 27. So the limit of f of x as x approaches 3 is 27. Yes, you can ask your question now.
Please, I just wanted to ask whether if you use anytime you use the long approach, you get the same answer as using the short
Yeah,
approach.
you'll get the same. You'll get the same.
Okay.
Yeah, whether long approach or you doing the direct substitution, those are properties we'll be looking at it next. Those are the properties of limits. So from the basics, we do the long approach, pick numbers that are closer and closer in this direction, numbers that are closer and closer in this direction, and then look at the behavior of the function. They should be approaching a certain point, the same value. Then that same value becomes a limit. But if they don't approach the same value, then it means that the limit does not exist. So you can either do the direct substitution or go through the long approach. It is through the long approach that we have the properties of limits, which we are going to discuss next. All right, so with that being said, let's look at properties of limits. We have seen that limits, we are doing what? Direct substitution. Wherever you see x, you put the value that so in the function, you put the value that the x is approaching in the function, and that gives you the limit of the function. And if the answer is undefined, then it means that the limit does not exist. But if the answer is a real number, which is not plus or minus infinity, then the limit does exist. So let's look at properties of limits. So we are going to shorten all those long English and write the limit as x approaches a of f of x. All right, so we shorten the limit as lim. As x approaches a, we are going to put that beneath the limit and then write f of x. This here is the same as finding the functional value of f of x at x equal to a. So we are going to essentially write f of a. Let's put this down as L. If we have a different function, limit as x approaches a of g of x, then this will be equal to g of a. Let me put this as L1. Let's write down this as L2. All right, so some of the properties are, if I have we have seen earlier, we just do direct substitution. The first property is known as the constant rule of limit. This means that if the function that the x is approaching, right, if we are evaluating the limit of a constant function as x is approaching a certain number, let's say the constant function is c, then this is equal to c. Why? This is because we said that limit, we're just doing direct substitution, meaning I need to see an x in my function for me to put the value that the x is approaching there. All right, so limit as x approaches a of c, since I don't see x here, we can create and destroy. We've done this several times. We create the x and destroy it by writing x raised to the power 0, as long as the value that the x is approaching is not equal to 0. All right, so we create the x and then destroy the x. We have seen that limit, we are doing direct substitution. So yes, now I see an x. So this is going to be c times a raised to the power 0. Any non-zero number, a raised to the power 0, will be 1. So here I have c times 1, and c times 1 is equal to c. So if the function under consideration is a constant function, Then the limit as x approaches a, it doesn't matter the value that the x is approaching, whether it is negative infinity, no, it doesn't matter. The limit of the constant function will always be the constant function itself. We'll look at examples of these. So that is the first property of limit. Second
please,
is,
please,
yes,
can you go over again?
with the constant property, constant function.
Yes, please.
All right, so if the function under consideration, earlier on, the functions that we've looked at were f of x is equal to x squared. This is not constant. It has a variable in it. And then we also looked at f of x is equal to 1 over x. This is not constant. It has a variable. Then the third example was when x is equal to x cubed. This is not a constant. It has a variable in it. We are looking at when f of x is just a constant. So maybe f of x is equal to just 5. We have seen that to evaluate the limit, all we had to do was here, our x was approaching 2, and the answer was 4. So it was just essentially finding f of 2, which is equal to 2 squared, and that is 4. For the second one, we just put in where I think x was approaching 0. We just find f of 0, and that is equal to 1 over 0, which is undefined. So in this case, the limit does not exist. For the third one, we are looking at f of 3 because we said that let x approach 3. So this will be 3 cubed, and that will be 27. But in the constant rule or constant property, the function under consideration is just a number. It has no variable attached. Limit, the shortcut that we have realized so far is wherever we see x, we are going to put the value that the x is approaching in there. So for instance, if we are finding the limit as x approaches 100 of 5, since there is no x in here, for us to put the 100 there, all right? And if our own understanding, if our understanding is that we're doing direct substitution, then I need to see the x in order to put the 100 there. We can create the x and then destroy it because the x was not there. So when we are creating it, we need to destroy it by writing x raised to the power 0. If we write this, then we have not changed anything within our function. This here is still 5. So it's still our constant function. Now we can apply what we know, and that is to evaluate the limit of a function. Wherever we see x, we are going to put the 100 there. So this gives us 5, we see 100, and then raised to the power 0. 100 raised to the power 0 will give us 1. So we have 5 times 1, and that will give us 5, which is the constant itself, meaning the limit of a constant is the constant itself. It doesn't matter what the x is approaching. As long as the function that you're trying to find the limit of is a constant function, the answer will always be the constant itself. And that is known as the constant rule of limit. Have I answered your question?
Yes, madam. Thank you.
Okay. Then let's look at the second property, which is known as the sum rule. Given the limit as x approaches a of the sum of two functions, so f of x plus g of x, second property states that we can separate sum. If you want to find the limit of the sum, this is the same as the sum of the limits. All right, so the limit of the sum of two functions is the same as the sum of their limit. Essentially split the functions into two and then apply the limits individually. So this is giving us the limit as x approaches a of f of x plus the limit as x approaches a of g of x. We've seen that limit wherever we see x, we put the a there. So the first term will be f of a plus the second term will be g of a. And this will be L1 plus L2. Since we said that let f of A be L1 and let G of A be L2. All right, and that is known as the sum property. If there are multiple functions that you're trying to find the limit of, and the operator between the functions is the summation operator, then one of the properties of limit is that you are allowed to separate the functions and apply the limit on the functions individually, evaluate the first function, evaluate the second function. The answer that you get, you sum them. An example of this, if we are to find the limit as x approaches 2 of maybe square root of 3. Now let's do step by step. Square root of x plus x to the power 4. If we want to find the limit of the sum of these two functions, then from this property, which is the sum property or sum rule, we are allowed to separate the functions, apply the limit on the individual functions. After we get the answer, we sum the two answers. So this is limit as x approaches 2 of square root of x plus the limit as x approaches 2 of x raised to the power 4. Limit, we have seen that wherever we see x, we are going to put the value that the x is approaching there. So from the first term, we'll have square root of 2 plus from the second term, we are going to have, 2 raised to the power 4. This will be square root of 2 plus 16. You are allowed to find square root of 2. I think you have 1.7172, and then you add it to. So approximately 17.7172, if I'm not wrong. Something in that form. But you are allowed to leave your answer in this form for academic purposes. And that is the sum property. Without being the case, can someone tell us what the subtraction property will be? If this is the sum, what will be the difference property?
Multiplication.
We'll just change
So
the
limit as x approaches a of the difference of two functions, f of x minus g of x. The difference property also allows us to apply the limit on the individual functions and then perform the subtraction. So this is limit as x approaches a of f of x minus the limit as x approaches a of g of x. Limit, we have seen that wherever we see x, we put the a there. So from the first term, we have f of a minus g of a. And that would be L1 minus L2. If f of a is L1 and g of a is L2. An example of this, to evaluate the limit as x approaches maybe 2 of x to the power 4 minus x to the power 2. To evaluate this limit, we have the difference of two functions. Therefore, we apply the difference rule or the difference property. And that is to apply the limit on the first function. So from the first function, we have limit as x approaches 2 of x raised to the power 4 minus the limit as x approaches 2 of x squared. Limit, wherever we see x, we are going to put the 2 there. So from the first, we have 2 raised to the power 4 minus, from the second, we have 2 raised to the power 2. 2 raised to the power 4, that will be 16, minus 2 raised to the power 2, that will be 4, and this is equal to 12. I need someone to help us with the next. If the operator between the functions is the product, what do you think the limit of such a function will be?
Now it will be
Is it
the limit
multiplication?
of
Yes, it's the
f of
multiplication, yeah.
Okay.
it will be the limit of f of x as x approaches a multiplying the limit of g of x as x
Very good.
approaches a.
So as x, so times here a and then g of x. Limit, we have seen that we're doing direct substitution. So from the first, we have f of a times from the second, we have g of a. So this would be L1 times L2. And this is known as the product rule or the product property because the operator between them is the product operator. Let's look at an example of this. Limit as x approaches 2 of square root of x cubed times x raised to the power 6. Or x raised to the power 5. That would be 64. All right, so limit, we have seen that wherever we see x first, but first of all, we say that this function here is made up of two different functions. The operator between them is the product operator. Therefore, the product property allows us to separate the function individually or evaluate the functions in the limit of the functions individually and then apply the product operator. So this is the limit as x approaches 2 of square root of x cubed times the limit as x approaches 2 of x raised to the power 5. Now we can apply the direct substitution. So here, wherever we see x, we are going to put the 2 there. So this will be square root of 2 cubed times x raised to the power 5. So we have 2 raised to the power 5. Because of the square root, the first we have 2 raised to the power 3 over 2 times 2 raised to the power 5. Indices, same base, multiplying. What do we do to the exponent? We sum them. So this gives us 2 raised to the power 3 over 2 plus 5. And that will be 2 raised to the power 13 over 2. And that will be the limit of the function. You are allowed to use your calculator from here, or you can decide to write your answer in this form. Any of them is allowed. Then we have the last one when the operator between them is the quotient. So limit as x approaches a of f of x divided by g of x. Here, since we have the quotient of two functions, we have also what is known as the quotient property, and that is we are allowed to separate the functions as they are and evaluate them. So here we have limit as x approaches a of f of x divided by limit as x approaches a of g of x, provided limit as x approaches a of g of x is not equal to 0. Because if the denominator is equal to 0, then the limit does not exist. Because if the numerator is non-zero and the denominator is equal to 0, remember under rational functions, if the top is non-zero, a, and then the bottom is 0, then this is going to be undefined. In such a case, we say that the limit does not exist. So if you have the quotient of two functions, yes, apply the limit at the top, apply the limit at the denominator. As soon as you see that the denominator go to 0, but the numerator does not go to 0, then the limit does not exist. So let's look at some examples and then cases where both numerator and denominator go to 0. In that case, what do we do then? All right, so examples of these. Limit as x approaches, say, 3 of x plus 2 divided by x minus 2. Limit, we have the quotient of two functions, and so we can apply the quotient property, and that is to apply the limit on the numerator. So this is limit as x approaches 3 on the numerator, x plus 2, divided by limit on the denominator. Hey, Nana, listen to your mother.
Nana want to eat fufu.
Nana, your mother make what? She brain. Don't come and trouble your mother, otherwise we'll be dikoto se. So limit as x approaches 3 of the numerator divided by limit as x approaches 3 of the denominator. Limit, wherever we see x, we are going to put a 3 there. So from the numerator, we have 3 plus 2 divided by, from the denominator, we will have 3 minus 2. The denominator does not go to 0, meaning the limit will exist. So this is equal to 3 plus 2, that is 5, divided by 1, and this is equal to 5. So the limit does exist, and the answer is equal to 5. Let's look at more examples. Limit as x approaches 4 of 3x squared divided by x minus 4. We have the quotient of two functions. Limit, we apply, if we have the quotient of two functions, then we can apply the quotient property, and that is apply the limit on the numerator. So here we have limit as x approaches 4 of the numerator, x, 3x squared, divided by limit as x approaches 4 of the denominator, which is x minus 4. Limit, where we see x, we are going to put the 4 there. So this will be equal to 3 times 4 squared divided by 4 minus 4. The denominator goes to 0. Numerator does not go to 0. So here we have 4 squared, that will be 16. 16 times 3, that will be 48, divided by 0. This is undefined. This means that the limit does not exist. If we had used table, you realize that one of them from the left, the value that the f of x will be approaching will not be the same as the value that f of x will be approaching from the right-hand side, meaning we are going to get undefined. Therefore, the limit does not exist because the answer we are getting is undefined. Let's look at another example. And then maybe you can walk me through this. Limit as x approaches 1 of 3x cubed divided by x squared minus 1. Can someone walk us through what will be the first thing we'll need to do here? I have the quotient of two functions. What property can I use?
The quotient property.
The quotient property. And what is the quotient property? Apply the limit.
The limit of 3x cubed as x approaches 1 over
Divided by
the limit
Divided
of
by limit of
x
x
minus
approaching
1
1.
as x approaches 1.
all right, then what else do I need to do?
So you put
Do the substitution.
X.
Wherever we put
limit back into 1 cube
Substitution.
over 1 squared minus 1.
And this will be 3 divided by 0. What is 3 over 0?
correct.
No, it's undefined.
Undefined. What does it say about the limit of the function?
It does not exist.
It does not
It
exist.
does. Okay, so the limit does not exist because the answer we got was undefined, and that is because only the denominator became 0. All right. One more example, then we look at the twist. The limit as x approaches 2 of x squared minus 4 divided by 3x. To find the limit of this function, we see the quotient of two functions. Therefore, we apply the quotient property, and that's to apply the limit on the numerator. This is limit as x approaches 2 of the numerator, x squared minus 4, divided by limit as x approaches 2 of the denominator, 3x squared. And this will be equal to 2 squared minus 4.
3 into bracket 2.
And this is 4 minus 4 over 6. 0 over 6.
6.
And what is 0 over 6?
Undefined.
Zero.
I knew I
Zero.
was going to get you there. I knew I was going to get you there. I knew I was going to get you there. So division is sharing, right? The numerator represents the items you are going to share. The denominator represents the people going to share the items. So this here is saying, I have 0 Ghana cedis. 6 people are going to share the 0 cedis. How much will each person get? Each will be equal to 0. However, if it's reverse, I have 6 divided by 0. The same principle. The denominator represents the number of people going to share. The 6 represents the amount of money we are going to share. So this fraction here says, I have 6 cedis. 0 number of people are going to share these 6 cedis. How much will each person get?
6.
Now it will not be equal to 6. How much you have 0 number of people going to share?
Nothing.
Nobody.
It's not possible.
Zero.
It's undefined because we don't know the people going to share.
Very good. It's undefined. You can define it because there are 0 number of people.
Yeah.
All right, it's undefined. 0 number of people. Do you know how much each person will get? There are no people going to get the 6 cedis. So if the denominator, simple trick is, if the denominator is is 0, then the answer is always undefined. However, if it's reversed, then the answer is equal to 0. What if I have 0 over 0?
It's defined.
Are you sure?
It's still undefined.
Undefined.
It's not undefined.
Not undefined. Because
So what is 0 over 0?
0.
Zero.
It's not 0.
One.
It's not.
Madam,
Hey, what's that one? Whoever said one,
madam, we can't determine. So it's you can't determine it.
you can determine it.
Yes.
You can determine. So we call this determine it.
Yes.
You don't have enough information. You don't have enough information to determine what is going on. Here says that you have 0 cedis. 0 number of people are going to share this 0 cedis. Determine how much each person will get. You cannot determine it because first of all, no people, no money. Therefore, if you're asking me how much each person will get, we cannot determine it. We don't have enough information. This here is meaningless. It doesn't make sense. You understand? You have 0.
Error.
Okay, so this is called the indeterminate form. When you have 0 over 0, it means you don't have enough information to determine what is going on in such a division.
Madam,
Yes, please.
Madam, please, there is one I want you to solve for us to see.
Okay.
The question is the limit of x squared minus 4 over x minus 2.
All right, so that is what we are going
to as x approaches 2.
Okay, we are going to do those things and how you are able to solve. Okay. All right, so let's look as x approaches say 1 of x squared. Let's make it minus 1. of x squared plus 2x plus 1 divided by x plus 1. Limit, we have the quotient of two functions. Therefore, the quotient property allows us to separate the function into the quotient form. So this will give us the limit as x approaches -1 of x squared plus 2x plus 1 divided by the limit as x approaches -1 of x plus 1. Now that we have separated it, we apply the limit. Limit, we have seen that wherever we see x, we are going to put the -1 there. So from the numerator, we have -1 all squared plus 2 times -1 plus 1 divided by, in the denominator, I have -1 plus 1. This will give us 1 minus 2 plus 1 divided by 0, and this is equal to 0 over 0. When the answer is 0 over 0, we call these indeterminate.
Indeterminate.
Now, if you have indeterminate, it means that the function is in the form in which you cannot determine what is actually going on there. Therefore, we have to go back to the function and then simplify the function. If you have the quotient of two functions, you apply the quotient property, which is apply the limit on the numerator, apply the limit on the denominator. If the answer is 0 over 0, we call 0 over 0 indeterminate. It means that you cannot determine what is going on here. And if we recall what we did when we met face-to-face, we realized that there were cases that we could cancel some of the asymptotes. Remember, if you're able to cancel the domain issue, then it is not an asymptote, but what is it?
A whole.
It's a, you remember.
A whole.
But if you cannot cancel the domain issue, then it is called what?
Undefined.
A vertical asymptote. All right. So if you have 0 over 0 in this case, you are definitely going to have some terms that you can cancel out in such a way that when you reapply the limit, you are not going to get 0 over 0, because 0 over 0 means we cannot determine it. Therefore, we need to go back to our function and then simplify our function. So we go back to the function, limit as x approaches -1 of x squared plus 2x plus 1, all divided by x plus 1. So since this gave us 0 over 0, we need to simplify the function. Therefore, we look at which part of the function that we can simplify. The denominator is a polynomial. Therefore, to simplify polynomials, you have to use factorization. However, factorization means you have to break it down into its least form. The linear is in the least form of polynomial in terms of factors. Therefore, we cannot break the denominator down any further. So we go to the numerator, which is the x squared plus 2x plus 1. It is quadratic. And in quadratic, we can factorize it into linear times linear. So we can't do anything about the denominator, but we can do something about the numerator. And this will be the limit as x approaches -1. What are the two factors of x squared plus 2x plus 1?
1 plus 1.
1 plus 1.
Yes, that's 1 and 1. Huh?
Are you is it x plus 1 or 1 plus 1?
One x plus 1 multiplying x plus 1.
X plus 1 and then x plus 1. All right, so now that we know the two factors, what else? What can we do here?
You cancel.
Yes. And then you cancel this out. So now our function is the limit as x approaches -1 of x plus 1 divided by 1, which is the same as x plus 1. Now I have the sum of x and 1. I have 1 here, 1 there. What kind of property can I use here to evaluate this limit?
The sum.
The sum, and that is because I have the sum of two functions. All right, so here, apply the limit on the first, plus apply the limit on the second. Limit, wherever we see x, we are going to put the -1 there. So from the first the function we get -1. What kind of property can I use to evaluate the second limit?
Constant.
A constant. What is the limit of a constant?
The constant itself.
The constant itself.
I have -1 plus 1, and this is equal to 0. So the limit does exist. The answer is equal to 0 and not 0 over 0. If you have 0 over 0, that is one of the sure way of knowing that, yeah, you need to go back and then do something about your function. In most cases, you are going to get a real number, and in some cases, you are going to get the limit does not exist. But as soon as you evaluate the limit and you have 0 over 0, 0 over 0 is said to be indeterminate. Therefore, go back to the function and then rewrite the function and then evaluate it. Now, let's look at the example the gentleman wanted us to try for him. So we have limit as x approaches 2 of x squared minus 4 divided by x minus 2. Here we have the quotient of two functions. So we use the quotient property. That is, apply the limit on the numerator. So limit as x approaches 2 of x squared minus 4 divided by the limit as x approaches 2 of x minus 2. Let me put this in the bracket so it doesn't confuse you that it's only on the x squared. Limit, wherever we see x, we are going to put the 2 there. So we have 2 squared minus 2 divided by 2 minus 2. 2 squared, that will give us, oh, this is 4. 2 squared, that will give us 4. 4 minus 4 equal to 0 divided by 2 minus 2 equal to 0. So the answer we are getting is 0 over 0. This is said to be in the indeterminate form.
Indeterminate.
All right, now once we have indeterminate, it means that we need to go back to the function and then simplify it. Simplifying it, the technique we use depends on the type of function we have. If the type of function we have in both numerator and denominator is polynomial, we know that to simplify polynomials, we use factorization. And so you go to the denominator, or whichever one that you prefer. Go to the denominator. What kind of function is it? It's a polynomial. I know to simplify polynomials, I need to use factorization, meaning break it down into its least factor. Its least factor for a polynomial is degree 1. Therefore, the denominator is already in the least form. I cannot break it down any further. And so the only term or the only function I can break down is the numerator function, which is quadratic. So in simplifying, because we are getting indeterminate, we go back to the function limit as x approaches 2 of x squared minus 4 divided by x minus 2. This is the same as the limit as x approaches 2 of x squared minus 4 is the same as x minus 2 x divided by x minus 2. Now, can we cancel some terms out? Yes, we can. We have x minus 2, x minus 2. They go away. Now I have canceled out the domain issue if we're finding the domain of a function. So I have x plus 2. Limit, wherever I see x, I am going to put 2 there. Or you can apply the sum property, treat this as one function, treat this as another function, apply the sum property. You still get the same answer as just applying the direct substitution. So I'll have 2 plus 2, and that is equal to 4. So the limit does exist. The answer is 4. Let's look at various forms. Let's look at one more, or actually two more. Limit as x approaches 5 of x squared minus 10x plus 25 divided by x squared minus 3x let's say plus 10. The plus 10, let me make it minus 10. All right, so we know that limit, wherever we see x, we have to put the value that the x is in there. Yeah, so first of all, before you do that, you need to apply the quotient property. But with time, you've realized that it will essentially be the same as just do direct substitution. But you will need to apply the quotient property first. So from the quotient property, we need to apply the limit on the numerator. If we apply the limit on the numerator, we'll have 5 squared minus 10 times 5 plus 25. Then we have divided by 5 squared minus 3 times 5, and then we have minus 10. This is equal to 5 squared will give us 25, minus 10 times 5 will be 50, then we have our plus 25. Divided by, I'll have my 25 minus 15 minus 10. This will be, okay, so we have 25, that will be 50, 50 minus 50, that will be 0. Divided by, here to be 25 minus 15, that will be 10. Then 10 minus 10 will also be 0. So the denominator is also equal to 0. So 0 over 0 is what we are going to get for if we apply the direct substitution. We are getting 0 over 0. 0 over 0 is said to be indeterminate, meaning we cannot use the function as it is to determine whether the limit does exist or does not exist. Therefore, we need to go back to the function and then simplify the function further. All right, so I'm going to rewrite my function limit as x approaches 5 of x squared minus 10x plus 25 divided by x squared minus 3x minus 10. All right, so if we simplify the numerator and then as well as the denominator, both we can simplify because they are in higher power more than 1. Therefore, we can simplify into 2 linear terms. Limit as x approaches 5. What are the 2 factors of the numerator?
5.
5.
5 and
5.
5.
Madam, negative 5.
Negative 5, negative 5.
So x minus 5, x minus 5. Like that?
Yes.
Okay.
No, 5x. Madam, 5x.
No, like that. Negative 5, negative.
Let's do it. So x squared minus 10x plus 25. Factorization, multiply the coefficients of the leading term by the constant term 25. 2 factors of 25, when you add, you get minus 10. So minus 5 and minus 5. So I have x squared minus 5x plus 25. I'll group these two and then group that 2. X out, I'll have x minus 5. Minus 5 out, I'll have x minus 5. So I have x minus 5, x minus 5. That is correct. Then the denominator to the same thing, x squared minus 3x minus 10. Multiply coefficient of the leading term by the constant term, that will be minus 10. 2 factors of minus 10, then when you add, you get minus 3. That will be minus 5 and 2. So for the denominator, I'll have the x squared minus 5x plus 2x minus 10 group this, and then group that. So x out, I'll have x minus 5 plus 2 out, x minus 5. So here too, I'll have x minus 5 and then x plus 2. You could also use your calculator to find them, like I showed you the other time. Just punch the functions into your calculator. It will give you the zeros, and then you write them down like this. These are the zeros. To get the factors, move the integers to the side of the x to join the x. That will give you the factors. All right, so now that we have the factors, let's see if we can cancel some domain out, the domain issues out. We have x minus 5. We have x minus 5. Therefore, we have limit as x approaches 5 of x minus 5 divided by x plus 2. Limit, now we still have the quotient. From the quotient root property, apply the limit on the numerator. That will be 5 minus 5 divided by, apply the limit on the denominator. That will be 5 plus 2. And this is equal to 0 divided by 7. What is 0 over 7?
0.
Undefined.
Madam Zero.
Zero.
Undefined.
Nine.
Guys.
Undefined.
No, it's 0. You have, okay,
It's zero.
so there are 7 of us, okay? 0 over 7 means there are 7 of us. We have 0, there are 7 of us. We have 0 Ghana cedis that 7 of us are going to share. How much will each of us get? 0. Because there's no money for us to go and share. The amount of money we are going to share is 0 Ghana cedis. And 7 of us are going to split this 0 Ghana cedis. How much will each person get? 0. Okay. But however, if it was the other way around, if it was 7 over 0, then this means there's 7 Ghana cedi. 0 number of people are going to share the 7 Ghana cedi. How much will each person get? That is undefined because you don't know the people. There are no people going to share the items. So here the answer is undefined. And if the fraction is 0 over 0, this means you have 0 people, 0 cedis. Determine how much each person will get. You cannot determine this because there's no money, there's no people going to share the no money. Therefore, 0 over 0 is said to be indeterminate. All right, so if we have polynomial
This question.
Yes,
Madam, please, can you scroll up so I write the question?
Okay.
Yeah, Madam, please, I want to ask a question. Well,
Oh, please, you can, yes.
yeah, Madam, please, with the product rule, I mean, is it okay to use like the way you are using the dots to represent the multiplication?
Yeah, you can
Is it
use the
okay to
time.
use?
I'm using the dot because you see how I'm writing my X.
Hello, madam. Hello.
Yes, please.
Madam, please, if you get let's say search work, before you work to know the answer is indeterminate. So all this working, will you get a mark for that or you don't get anything?
Hey, you are already worrying about marks.
Because for you to work before you know it's 0 over 0, there is indeterminate. Before you go back to factorize, I don't know if you get any marks, like you not getting anything.
Is it Alfred that's speaking?
Yeah, this is Alfred, madam.
Who else is also okay? So it's okay. Yeah, Alfred. Yes.
Madam.
Yeah, you will get marks.
Okay.
I don't know who traumatized you with the
because it's many for you to work to know before it's it's not indeterminate. Then you go back to factorize. Hey, Radif.
Yes. Yes, you need to show why you are factorizing. I do understand your point, because then you will do it on your, where is it? Yes. Here, you need to show this first. You get marks for this. So don't just jump in. Okay, don't just jump in and come here. You need to show why you are doing this. And to show why the reason we are doing this is because we got indeterminate. This you get marks. But if you just jump ahead, yes, you good. Yeah, you understand that the thing is going to be indeterminate, but I need to see why you are doing that. Because you'll get marks for it.
Okay, thank you.
Yes. Yes, please. Okay. Is there any other question? All right, so if the functions involved are polynomial functions, polynomial functions, for example, P of X divided by K of X, and you have 0/0, then to simplify it, because we are getting indeterminate, this will be indeterminate. To simplify the indeterminate, when the functions involved are polynomials, both top and down are polynomials, then we use factorization. Because factorization is used when you want to simplify polynomials. Now let's look at cases where one of them is not a polynomial, but it is radicals, or what is known as the square root. Okay, so if we have limit as x approaches, say 1, or square root of x minus 1 divided by x minus 1. To find the limits of this function, let's go step by step. I know you know it, but let's take baby step. Here, we apply the limit on the numerator, apply the limit on the denominator. And this is because the function is in the quotient form. So our first thing is to apply the quotient property. Limit on the numerator will give us square root of 1 minus 1 divided by limit on the denominator will give us 1 minus 1, and that will be 0/0. 0/0 is indeterminate. And when we have indeterminate, it means that we need to go back to the function and simplify it. So let me rewrite my function. Limit as x approaches 1 of square root of x minus 1 divided by x minus 1. To simplify this function, we go to the denominator. The denominator is a polynomial. It's in the least form. Therefore, we cannot break this down any further, because you cannot factorize it any further. To simplify polynomials, we use factorization. So we go to the numerator function. This here is known as a set. And to simplify sets, we perform what is known as rationalization. The first step towards rationalization is known as conjugation, meaning pick the function and find its conjugate. Conjugate means that rewrite the entire function, but change the operator between them. And so if the operator between the the function is a subtraction, its conjugate will be the same expression, but change the subtraction into addition. So for instance, if we are finding the conjugate of square root of a plus b, the conjugate will be square root of a minus b. And if in the original function you have square root of a minus b, the conjugate will be square root of a plus b. After finding the conjugate, multiply both numerator and the denominator by the conjugate of the set. That is what is known as rationalization. Find the conjugate of the set, multiply both and top. I would have asked why the top and then the down, because we are going to multiply the original function by something which is not equal to 1. And we know that if we are introducing something which was not originally there, after creating it, you need to destroy it. And so since we are going to create something which is not there, after creating it, we need to destroy it. So whatever you do to the top, you have to do the same thing to the down. Whatever you do to the left, you have to do the same thing to the right, so that you maintain equilibrium, or you maintain balance. All right, so since we are simplifying the numerator, we perform conjugation. And the conjugation is write the same function, but change the operator between them, which is a subtraction, into the addition. So the conjugate of square root of x minus 1 will be square root of x plus 1. Multiply this top here by the square root of x plus 1. So here I will have times square root of x plus 1. We don't leave it like that because the square root of x plus 1 was not originally there. So after creating something which was not there, after creating something which was not originally there, we need to destroy it. So we divide through by x, square root of x plus 1. Then multiply the top, multiply the down, and then you keep going. All right, so we are performing conjugation because we cannot factorize the denominator. It's in the least form of a polynomial. We cannot break it down any further. We look at the numerator. The numerator is a surd. To simplify surds, we use rationalization. Rationalization means that we need to first of all find the conjugate of the surd. Conjugate of this surd here, which is square root of x minus 1, is square root of x plus 1. Since we are multiplying this surd here by something which was not there, after doing this creation, we also need to destroy it. That is how come I have both top and then down. I have one fraction multiplying another fraction. Therefore, we multiply the tops divided by multiply the downs. So this is the limit as x approaches 1 of square root of x minus 1 times square root of x plus 1 divided by x minus 1 square root of x plus 1. Now, here is a little bit of trick. I have the product of two functions, both at the top and then the down. However, the only product that I am going to expand is the one at the top. I am not going to expand the one at the down because if I expand the one at the down, I'll have to come back and do refactorization. And so once you look at where the surd is, all right, look at where the surd is and where its conjugate is. That is only the term that you need to expand. Do not touch the part where one of them is different from the other. No, don't touch this. If this was at the top, don't expand it. Leave it as it is. But expand the part where you have the terms being conjugates of each other. Don't touch the part which is not conjugate of each other because you will find yourself into trouble. So once you've done the conjugation, put the tops together, put the bottoms together, the only part that we are going to expand is the part where I see the conjugate so that my work becomes easier. So from the top, I have the limit as x approaches 1. Now we have algebra on our hands. If I look at the top, it looks like something of the form a minus b times a plus b. The terms are the same. The only difference is that the signs between them are alternating. This is known as the difference of two squares. If I multiply a minus b by a plus b, the answer is always a squared minus b squared. So instead of picking this, multiply by that, this, multiply by this, then you come and pick the minus 1, multiply by square root of x, Minus 1 multiplied by 1 and simplifying.
Let me say 3 also. And send me to 4.
Combe, please mute your mic, please.
All right, so instead of doing,
want to confuse us. We are already confused, but he wants to confuse us more.
see, he's buying something. All right, so instead of doing the 1 by 1 multiplication, we are going to employ algebra, which is a very powerful tool, and then write it in this form, which will always be the difference of 2 squares. So I don't need to multiply them 1 by 1. All I have to do is to pick the first term and square it. The first term is square root of x. So I'll pick this term and square it. Then minus, I'll pick the second term, which is 1, and then square it. And that is it. I don't need to multiply 1 by 1 because the two functions are the same. The signs between them are alternating, and it's always the difference of 2 squares. Divided by, like I mentioned, do not expand the terms that are not the same, which are alternating. So I'll maintain my x minus 1 by square root of x plus 1. From the numerator, limit as x approaches 1. I have square root and then square. Square root and the square will always cancel each other. Therefore, I am left with just x here. Then I have minus 1 squared is 1, so x minus 1. Divided by, I have my x minus 1, and then my square root of x plus 1. Now you see why I did not expand. I have x minus 1 here, I'll be left with 1. X minus 1 here, that is 1. So this is the limit as x approaches 1, 1 divided by square root of x plus 1. Limit, wherever we see x, we are going to put the 1 there. So this will give us 1 divided by square root of 1 plus 1. And that will be 1 divided by square root of 1. Sorry, square root of 1 is 1. 1 plus 1, that is 2. So the answer is 1 over 2 after performing rationalization only, because the denominator function was a polynomial function. Let's look at another example. Maybe,
Madam,
yes.
Madam,
Yes.
please go up small. I saw something here.
Okay.
Yes. Madam, I can see the square root of x plus 1, and at the denominator, I can also see square root of x plus 1. Can't I cancel them out?
You mean these? Sorry, you mean these?
Yes, please.
And then if you cancel them out, you are back to the problem again. If you cancel these out, you are left with just this, which is the question itself. You are back to 0 over 0. No, you can't cancel them out. You need to multiply just the top, multiply this by that. Otherwise, you are back to the problem again. So don't cancel those out. Yes.
Hello, madam.
Yes, please.
Madam, please, can you go up a little bit for me, please?
Okay.
A little bit, please. Please, okay. No, when you consider you had the one over square root.
Oh, okay.
The one, then is this one? Yeah, this one. Please, when you substitute the 1 over square root 1 plus 1, please, like we had 1 over square root 1 plus 1. Please,
yes. And square root of 1 is 1.
It's 1. But then we cannot add the 1 plus the square root 1.
You cannot add what?
The square root 1 plus 1.
Yeah, so you find the square root of 1. That will be 1. So here is 1 over square root of 1 is 1. Then I have my plus 1. 1 plus 1 is 2. So the denominator is 2. So I have 1 over 2.
Okay.
So, Madam, please, so anytime, let's say you have square root of 10, you have to find the square root of 10 before you add it to the
Yes, yes, you have to find the square root of 10 and before you add it to the 1.
Okay, madam.
Yes,
Thank you.
like that. Okay.
Hello, madam.
Yes, please.
So sorry. My question is not really on what we are doing. I wanted to ask,
Uh-huh.
where can we apply this in our daily lives, please?
Oh, these are limits. We are looking at behavior or function. So not like necessarily in our daily life, but if you are analyzing scenarios where things are changing, you want to look at the behavior. For example, is there assignments approaching soon? Yeah, there's an assignment approaching soon on the LMS. All right. So for example, if we're looking at the performance level of the LMS server, as the number of students accessing the server approaches a certain number, what will be the performance? That is what limit is looking at. So we're not necessarily going to use it to buy something. No, it assesses or evaluates the performance of a system as the amount or as the number of load on the system changes. So for time, as there are no assignment due or deadline approaching on the LMS, the performance level of the server will not be the same as the performance level of the server as assignment deadline is approaching. So maybe 11:59, an assignment deadline is coming up. Most of the time, students will wait till close to 11:59. So limit is we're looking at as the time is approaching 11:59 and the number of students is increasing, maybe by 11 p.m., number of students accessing the server is say 50. 11:15, number of students accessing the server is say 70. You notice that as time is increasing, number of students accessing the LMS is also changing. Limit is looking at the performance level of the server as the amount of load on it is getting larger and larger. We could also look at it in terms of database. You issue a query on a database, all right? As the number of queries that you are issuing on a database is getting larger and larger, what is the response time? That is limit. We are evaluating the response time in terms of database. You are evaluating the response time of the database as the number of requests or as the number of queries. Maybe it's 10 queries. How long does it take for me to get a response? As the number of requests or as the number of information I want from the database is say 100. How long does it take for me to get a response? That is what limit does, but it's not something that you can just pick it and then this limit that we did I'm able to use it to buy stocks on the market. No, you will use limit to assess performance. We use limit to evaluate behavior of whatever it is that we're looking at. So it's not something you're going to see in your daily life as you are working.
Madam, please, one more question, please.
Okay.
Madam, please, I don't know if you can go back to the original question. Please, before you solve and we had the
indeterminate.
Yes, please. Please, when we change the sign, that's opposition sign from minus to addition.
Plus.
Please, when you substitute the let's we had square root 1 plus 1 over 1 plus 1. Please, can't we just add the square root 1 plus 1 and then 1 plus 1 and we get something like square root 2 over 2? Is it possible that way? I don't know.
No, then you will still have those. Then you will still have this to deal with. Because you have this and then you have that. If you substitute the 1 in this function as it is at the moment, yes, you are going to have 2 over 2, but you're still going to have 0 here times you're still going to have 0 here. So the numerator will still be 0 times 2, that is 0, divided by 0 times 2, that is 0. You still have 0 over 0. So you've not solved anything at all. So no, once here, you cannot substitute the limit yet. you need to multiply the top, but leave out the down, because, well, it is a simple technique as you could have, but you still have to come back and redo factorization. Multiply the top only because it is the top that is conjugate of each other. And then you leave out the denominator. You cannot substitute the limit over here and then you leave this side out. No, it's also part of the function. You can do that.
So, madam, please.
Yes.
So, madam, please, always we should be working at the top.
No, you should be working at where the functions are conjugate of each other.
Okay, all right.
Because sometimes you'll be at the top, sometimes you'll be at the bottom. So always work on where the conjugates are. Yes, please.
Can you please give me a further explanation on when we need to rationalize limit functions like what we saw?
Yes, we
need to rationalize them.
When you have sets, that's when you rationalize. When you have polynomials. When you have polynomials.
What if when the numerator is a radical? Do we have to rationalize it?
Yes. As soon as you see a radical or you see a set, you have to rationalize.
So we need to check the numerator and at the same time the denominator.
At the same time, the denominator as well. Yes, you need to check both. And then you perform the rationalization.
Thank you. All right, thank you.
So let's look at another example. X squared minus 9 divided by square root of square root of x minus square root of 3. Let's look at finding, evaluating this limit here, step by step. This is the quotient of two functions. So the first property or the first rule that we'll be applying is the quotient property. And in the quotient property, apply the limit and the numerator. So wherever I see x in the numerator, I'm going to put the value that the x is approaching there. X is approaching 3. So I have 3 squared. Minus, I have my 9. So minus 9. Divided by, apply the limit in the denominator. Wherever I see x, I'm going to put 3. So here too, I have square root of x, which is square root of 3 minus square root of 3. In the numerator, 3 squared, that will be 9. 9 minus 9, that is 0. Divided by square root of 3 minus square root of 3, that is also 0. This is indeterminate. When you have indeterminate, you have to go back. It means that the function is in the form that is not easy for you, or is not in the form that you can easily determine whether the limit exists or does not exist. So you go back to the function and look at the various parts of the function. Employ the appropriate technique. For polynomials, you perform factorization. For sets, you perform rationalization. So we go to the function. Let me rewrite the function. I have limit as x approaches 3. Data, I have a set. In the numerator, I have quadratic. All right. And so you notice that I have a combination of these two functions. To simplify polynomials, we use factorization. But the denominator I have is set. Therefore, the technique we are going to use here is both the factorization and the rationalization. In the factorization, we use that in the numerator function because in the numerator function, I have squares, which means higher power more than 1. I can break it down into linear forms. However, in the denominator, I have a set. Therefore, to simplify that, I need to perform rationalization. If the numerator had been just this, then I will still perform rationalization because I have said. it doesn't matter where the said is. It could be at the top or at the down or the denominator. You still have to perform rationalization. As long as you have a said in there, you need to perform rationalization. The top is also higher power more than 1, which is a quadratic. Therefore, I need to also break that one down. And to break down polynomials into linear forms, we use factorization. So from the top, I need to perform factorization. And the factors of x squared minus 9 are x minus 3 and then x plus 3. Divided by my denominator, square root of x minus square root of 3. So now that I've factorized the numerator, you realize it still doesn't cancel anything out. It doesn't help anything. No, it doesn't. So I still need to perform my rationalization. And the rationalization is take the said, find its conjugate, and use that conjugate to multiply both the top function and then the bottom function. So here I have times the conjugate of square root of x minus square root of 3 is square root of x plus square root of 3. Whatever you do to the top, you have to do the same thing to the down. Square root of x plus square root of 3. So we put together the numerators, which is my x minus 3, x plus 3. Then the top, which is square root of x plus square root of 3. Divided by, put together the down, square root of x, square root of 3, square root of x, square root of 3. Now we need to, from here on, we need to be strategic. Do not touch the top. Why are we not touching the top? Because what is here is not the same as what is there. They are not the same or conjugate. Therefore, if you expand this and that, you are going to find yourself into trouble. At the end, you won't have anything to cancel out. And so do not touch the parts that are not conjugate of each other. All right, that is being strategic. And so the only part that we are going to touch is the term at the denominator side. So I'm going to maintain my numerator as x minus 3, x plus 3 times square root of x plus square root of 3, divided by, multiply what is inside this bracket by what is inside this bracket. Once again, be strategic. It's not everything that you need to do. If I look at what is inside the bracket, it looks as if it's of the form a minus b times a plus b. And this is always a squared minus b squared. So instead of multiplying the root of x by root of x, come back, multiply root of x by square root of 3. Then you pick the minus root 3 multiplied by root x, the same minus root 3 multiplied by root of 3. We can, from the difference of two squares, pick this and square it, minus pick this and square it. And that would be the same as doing the 1 by 1 multiplication. So I pick the first term, which is the root of x, square it, minus, I'll pick the second term, which is root of 3, and square it. This is limit as x approaches 3, x minus 3, x plus 3, square root of x plus square root of 3, divided by, I have square and the square root, they cancel each other. Square and the square root, they get rid of each other. So from the denominator, I have x minus 3. Now you see why I did not touch the numerator, so that you can see that this is the term that I need to cancel it with. From the numerator and the denominator, I have x minus 3 here, x minus 3 there. So this gives me the limit as x approaches 3 of x plus 3 square root of x plus square root of 3, all divided by 1. By any number divided by 1 is the same number. Now limit, I have the product of two different functions. The product property allows me to evaluate the limit of the first, limit of the second, and then after that, multiply them. So here, limit on the first will be 3 plus 3. times limit on the second will be square root of 3 plus square root of 3. 3 plus 3, that will be 6, times square root of 3 plus square root of 3, that will be 2 square root of 3. And this is 12 square root of 3. So the limit does exist. It is 12 root of 3 instead of 0 over 0. Any questions on that? I'm sure you don't by now.
Madam, no question, but I have some example if we can try this.
Yes, we can try this. I think at time we can try it before we go. Yes.
Please, can I give?
Yes, please.
Please, the limit is 4 minus x squared, all divided by 3 minus root x squared plus 5.
Is it all under the root?
Yes, please. As x approaches 2.
All right, so wherever we see x, we are going to put a 2 there, right? So from the numerator, we'll have 4 minus 4 divided by, from the denominator, we'll have 3 minus square root of, if you put a 2 here, that'll be 4, 4 plus 5, that is 9, square root of 9. And this will be 0 divided by square root of 9, that is 3, 3 minus 3, that is 0. So we have indeterminate. We need to simplify our function. So limit as x approaches 2, simplifying, if we look at the numerator, I see the difference of 2 squares also. So I can factorize the numerator, and that will be 2 minus x times 2 plus x divided by, I have my 3 minus square root of x squared plus 5. However, even after factorizing the numerator, I still can't get any terms to cancel out. So I'm still, if I apply the limit again, I'm still going to get 0 over 0. And so the next thing is to rationalize, and that is because I have a z. And the z is located at the denominator side. To rationalize, find the conjugate of the z. Since the z is 3 minus root of x squared plus 5, its conjugate will be 3 plus square root of x squared plus 5. We multiply both top and down by this conjugate here. Right, so multiply both and top because it was not originally there. So we have times 3 plus square root of x squared plus 5 divided by 3 plus square root of x squared plus 5. This is limit as x approaches 2 of 2 minus x, 2 plus x, then multiplying the 3 plus square root of x squared plus 5 divided by 3 minus root of x squared plus 5, 3 plus square root of x squared plus 5. Since the numerator does not contain the conjugate, I am not going to simplify it or expand it, and then just leave it as 2 minus x, 2 plus x. 3 plus square root of x squared plus 5, all divided by, in the denominator, I see the conjugate, and it is the difference of 2 squares. So all I have to do is to pick the first term and square it. That'll be 3, square it, minus, pick the second term and square it. So square root of x squared plus 5, and then square it. Limit as x approaches 2 of 2 minus x, 2 plus x, 3 plus root of x squared plus 5, divided by 3 squared will give us 9, minus square and the square root, they cancel each other. So I'll have x squared plus 5. if you open the bracket, then the minus affect the x squared, and it also affects the 5. So at the denominator, I'll have minus x squared minus 5. 9 minus 5, that'll give us 4. So limit as x approaches 2 of 2 minus x, 2 plus x, 3 plus root of x squared plus 5 divided by 4 minus x squared. Now you notice the 4 minus x squared is also the same as 2 minus x, 2 plus x. So this will cancel all of that. And you are left with the limit as x approaches 2 of 3 plus square root of x squared plus 5. Now limit, wherever you see x, you put a 2 there. So this is 3 plus square root of 2 square will be 4 plus 5. 3 plus square root of 9, 3 plus 3, and the answer is equal to 6. Are you sure this is not part of the limit questions?
Thank you, madam. Thank you, madam.
Okay.
I was trying to check my answers. Thank you.
All right. Please, if you have any questions, jot them down. Our time is up. I think you have another class. Jot them down, and then
Madam.
we can.
Please,
Yeah.
can you calm down a little bit? Can you please calm down?
Madam,
it seems after we left the product property, we came to quotient. We didn't go back again.
Well, please calm down, ma'am.
I should keep. Okay.
Yes, ma'am.
Hello, madam.
Yes.
Please, what if you can
ma'am, please,
from
okay.
the
No,
question?
please, ma'am, you have gone too much.
You say?
Come up a little. Please come up a little bit. Yeah, it's okay. It's okay here. Thank you.
Madam.
Yes.
Yeah, please, what if you can detect from the question straight that this thing, when you solve, when you put, let's say, the lim values, let's say lim of x approaching 2, when you put it in the equation, you get 0 over 0.
Mm-hmm.
What if you can detect straight, so you don't have to do this thing, solve for that one and you
No,
go
I
straight
think
in?
I've already answered this one, and that is for academic purposes. You can just, you can just jump ahead and start rationalization. No, you have to show why you are doing the rationalization. And you are doing the rationalization because you saw that the answer is giving you 0 over 0. You need to show that first. All right, so you need to do this part, the current part where you're seeing. You need to do this part. Yes, sometimes you can just see that it's going to give you 0 over 0, but you need to do it first. You get marks there before you start doing the rationalization or you start doing the factorization. So you need to show it first. No, you can't do that. Yeah. Otherwise you get everything correct. You walk out of the exam hall. I should be getting 100 over 100. And the script comes out, and then you got 70 over 100, and then you're wondering why. I did everything correct. Yeah, that is because you jumped important steps, and that important step is why are you doing this? You need to show, and to show it, you just need to write it down. You got 0 over 0. So every piece of information counts.
Okay, so madam, please, as a method of showing, and in case you got it wrong, are you getting the whole question wrong, or during the process?
No. So assuming is this question that came, this one that the gentleman gave us, this you get some marks. Some your pluses, your minuses somewhere, tricked you. Instead of getting your final answer to be 6, maybe your final answer was something else. But everything just logical. If the whole thing is 10%, then you get like 9 over 10.
Right, madam. Thank you.
Yeah, so don't jump steps. All right, so yes, jot down your questions and then we can. Yes, the lady was speaking.
Yes, that is Sedinam.
Oh, yes, class rep.
Yeah, madam, please, the lecturer is waiting for us to join the
Okay, yeah,
we are using
okay.
the same link.
All right. Thank you very much. Okay.
Madam, we are not done writing.
She will post it, so please.
Madam,
Yes.
please. The last one, the bottom cry to see the answer.
Madam is gone because we are having the next session, so she'll be posting it.